Hi everyone, we are Group 10 and I am Mariana Lozano, one of the electrical engineers in the group, here to discuss our middle term demo for our automated indoor nursery. We have split our presentation into three main subjects. The first is the design of our automated indoor nursery, then the key engineering specifications, and finally the overall functionality of our system. Part 1 is the automated indoor nursery design. This is our enclosure so far. In the bottom we've got the drain pan with the water pump inserted with a USB connection that will connect to our PCB. The middle level has our pots with the drip irrigation system in it. Up above our 4 lights will hang from the corrugated sheet. The back has an adapter that will push the water back into the drain pan, and when water needs to be changed, they just have to unplug the water pump, pull out the drain, fill it back up, and then can push it back in. And the vinyl will come at the end because we don't want to ruin it by putting the enclosure all together right now.
I will be going over all the components within our design. First off is the weather shield. The weather shield is a temperature, pressure, and humidity sensor. We will also have a light sensor which will tell the user how much light the plants are getting. We will also have a camera module which will take photos of the plants and send it to the user. A water level sensor which will tell the user how much water is left in the enclosure. A pH sensor which will tell the user what the current pH levels are within the soil. And a Wi-Fi module which will allow us to send all this information to our website.
For the advanced design, we built a merge stack application that is built on a NoSQL database using MongoDB, React as our front-end framework, and an Express node server. Along with a React application, we also are implementing a progressive web application, which will make the mobile experience and desktop experience more seamless, as well as having deployed it through Heroku.
Part 2 is the key engineering specifications. Here are the market specifications and where we are at with them. The weight of our system is still to be determined. We met our size specification because we required less than 10 cubic feet and our enclosure is 9.39 cubic feet. The size of our drain pan is 24 inches by 24 inches and holds a depth of 2 inches of water. The max input voltage we have is 12 volts DC, and our specification we had set to about 24 volts DC. The website is also properly displaying data, just need to finish putting it all together after our PCB is all done. Lastly, with the drain pan and vinyl cover on our unit, does not leak.
In this slide, I'll be going our engineering specifications. Right now, we're still currently trying to figure out the readings after the recalibration on the sensors. Some of the values are still coming up very weird. We also need individual power sources for each of the 16 by 16 lights. The Wi-Fi module also needs to be tested in the upcoming week with the new PCB. We actually just received the new PCB, so we're still a little bit behind on that. The water control is controlled through drip irrigation, so it also must be filled to a certain point for the pump to continue to work.
This is the Weather Shield demo. We are running sensors HTU21D, MS5637, and MS8607, as these give accurate temperature, pressure, and humidity readings. We were testing using the Arduino Mega build. These are the connections. This is the test that we ran for the light sensor, a test for visible light, infrared light, and UV light. By shining our phone on the sensor, we can see the values for the visible and the infrared light go up, indicating that it is, in fact, registering these values from the light source. Now we remove the phone with the light source attached, and we can see that the values go down.
For the camera functionality, it's still a work in progress. We brought in the packages required to start coding it. The front end and UI design for handling images hasn't been implemented yet, but there are methodologies that we are deciding on, either with a Bitbucket to store the data or encoding the data as a base64 encoding language to save on space when we do save the images.
Here you can see we put together our drip irrigation system. We tested it 10 times in each drip to see how long we will have to program the water to turn on for these plants to receive 1 inch of water a week. Our average after all the testing came out to approximately 10.29 seconds per pot.
As mentioned before, we are still having some troubles reading some of the sensors, the pH sensor being one of those, but we were still able to get some readings. This is before calibration. This still needs to be worked on, but with regular water, we had a value of 10.4. With soap water, we had 9.03, and with lemon water, we had 10.35. So as you can see, we are getting different value ranges, but they are not at the correct level. So hopefully within a little bit more calibration, we should be getting the correct readings on those.
This is the test that we did for one of the 16 by 16 RGB lights that we're going to use for our enclosure. It is right now current limiting. It operates on 5 volts. We just wanted to demonstrate a little bit how by cranking the knob up and down, we can determine how much power gets fed into these LEDs and how that determines the brightness of them. This is the demo for the liquid level sensor. Right now, for the test, we were using a water bottle that had a little bit of liquid left. That's why the output's 1, as in true. Inside there, we can see that there's a very small amount of water left, but there is some. As we pull out the sensor, we now check the reading on the display port. We can see now that it's 0, indicating that it's false, that there's no water left.
So our website does persist data in the database where we can send and receive data from the database. We are using state loading on certain pages in order to reduce page loads, where if information is updated from the database, all we do is reload the component as opposed to the entire page. We also introduce website caching through a webpack, and that allows assets that are larger to be cached. So on first load, those assets are stored, and then when you return to the website, they are retrieved from the local storage. This also increases page optimization, page load time optimization, and the progressive web application allows you to download the application either on your desktop or your mobile device, just like from the web store on a mobile phone or on a desktop.
Part 3 is the overall functionality demo.
So on the next slide, we're just going to go through the website flow where the user can log in, they can add a device, they can add plans, and we'll look at the live database and see that the data is stored there currently. So for the website walkthrough, as we start the website, we will reload the page. We'll quickly sign up with a brand new email address. And there is validation for both the email address and the password. And then we can see when we log in, we create the brand new instance in the database of that user. We're then redirected into an authorized dashboard page, which you cannot access unless you are logged in. Once you are logged in, you can go ahead and add a device ID. This device ID will be important because it will correspond to the Wi-Fi module in particular, and it'll allow you to add plans to that particular Wi-Fi module, which will be related to the PCB. We can see that we added our herb garden here, and as we go to the next page, we can start adding our plants. Currently, the first one is state-based loading. So as we enter our information, it'll automatically update with the new information, and we will just quickly go through and add the rest of them. And then if we look on the right hand side, the database is updating with the new information. For the actual progressive web application, on the top right of the URL bar, you can see a monitor screen with a download button. We'll go ahead and click that, and it'll allow us to install it on our PC, and it'll make the UI much larger,
to replicate a mobile experience. And you can also do this on your phone, where you download it as an app tile on your phone. So for the chart functionality, it is still part of our final goals. We do need to get the sensor data from our application, since the timestamp is created when the data comes in. The place in the database does exist. We do need to build the UI for that, but the expected data structure is built for Chart.js to display our data.
So this slide is going to cover PCB functionality. During this time frame, we weren't able to get the PCB in person, so sadly we won't actually have an image included in our slides. But we decided to go with the EasyEDA 3D image of our PC board, so we can give you a good overview of the components in our PCB. So the most important component in our PCB is our microcontroller. That is the Arduino 2560. That is the brain of this PCB. The second most important thing on this board is the relays. Those are going to be in charge of the lights and the pumps of this enclosure. They are going to be the ones that are in charge of powering on those components and feeding data to them. In the top left corner, as you can see, that is our USB Type B. That's its main focus is flashing the components on the board. So that is how we're going to be able to program the components to do what we want it to do. And fourth is last but not least, is the barrel plug. The barrel plug is what's going to be powering on this entire PCB. So this slide is a continuation of the last slide. We're going to be going over more functionality of our PCB. First up, we're going to be going over the connectors of the 5-volt peristaltic pump and the RGB squares. Those two blue squares right there, those are what's going to be powering on the peristaltic pump and the RGB squares. The next is the 5-volt water pump, which is located underneath the enclosure and going to be feeding water to the top. Number 7 is the voltage regulators. These two components are what's stepping down the voltage to properly power the components throughout the board. And number 8 is our Wi-Fi module. The Wi-Fi module is used to collect all the data from the sensors and then sending it to our website for the user.
Thank you for listening to our Midterm demo, and we hope you enjoyed it. Any questions?